In this video, we're going to talk about the central limit theorem. Understanding the central limit theorem is absolutely critical to understanding the larger concept of hypothesis testing. In many ways, the central limit theorem makes the logic of hypothesis testing possible. So we're going to be teaching you a major concept here. So pause the video if you need to at any point and re-listen to it if you think that'll help you. I'm going to start off with a simpler question. Why do researchers have to work with samples when really they're interested in populations? Again, if you need to pause the video, do so. Generate an answer. Well, the reason why researchers work with samples when they really are interested in populations is that measuring an entire population is really impractical and in many cases impossible in most real-world situations. So what they do is they take a sample from that population. And the purpose of this sample is to represent the population. What I mean by that is the answer, the data that I collect, the answer, the mean, the results that I get from the sample should be the same as the answer I would get if I were to measure the entire population. Another simple question is, what major problem results when researchers use samples instead of populations? The answer is sampling error. Measuring sampling error is really the point of this video and several subsequent videos. There are many different ways to measure sampling error, and we're going to learn one in this video. But the idea or the concept of measuring sampling error is, again, what makes hypothesis testing possible. What is a distribution of sample means? What I've drawn here is actually a population distribution. It has a known mean of 50 and a known standard deviation of 10. And I know that this population is normal. And so because it's normal, I can draw in 50 in the middle and then take standard deviation steps to the right and to the left. And so the standard deviation was 10. And so I'm going to move to the right and to the left in 10 step or 10 unit increments. So the center is 50, one step up is 60 and 70 and 80 and so on. Now, as we've done in a previous video, what we can do is we can take this raw square number line right here and we can convert it to a z square number line right here by using this equation. Z is equal to x minus mu divided by the standard deviation. Just to go through one quick example, if we want to generate how the 0 was generated, we'll take 50 for x, the score, minus 50 for the mu divided by 10, that's going to give us 0. 60 would give us 1, 70 would give us 2. Again, the z-score number line is pretty easy to generate. All you're doing is finding out what the center is, which is always going to be 0 in a z-score number line. The mean is always 0 in a z-score number line. And then one step up, one z-score up, is going to be equal to one standard deviation step up on the raw score number line. At this point, you probably don't even need the formula anymore to generate those two curves, or those two number lines. All right. Now what I'm going to do is I'm going to generate a distribution of sample means using a specific sample size of 25 people. Now, what is a distribution of sample means? Well, it's a distribution. In other words, it's a list of scores. It's a bunch of scores. But it's not scores anymore. It's sample means. So the literal definition of a distribution of sample means is it's all possible sample means from a given population with a based on a given sample size. I'll go through that again, but I'm going to demonstrate it first. So I'm going to take a sample of 25 people from this population over here and generate a distribution of sample means. So I took 25 people and then I computed the mean of those 25 people, and that generated a score of 49, and I've written that on this number line over here on the right. Now I'm going to take those 25 people, throw them back into the population, and then I'm going to take another sample of 25 people. This time I got a mean of 52. Take those 25 people, throw them back into the population, and this time I'll take another sample, and this time I got a mean of 50. I'm going to do it again, take everybody, throw them back in, take another sample of 25, find their mean. This time I got a mean of 50. I'm going to do it again. This time I got a mean of 51. I'm going to do it again. This time I got a mean of 49. And you can see what's happening. I'm just going to keep doing this and keep doing this until I generate all possible combinations of 25 people and then find their mean. Now let me go into that all possible combinations thing one more time. Let's say that this is Bob. He has a score of 46. I need to pair him up with every other person in the distribution, every other possible combination of another 24 people to generate all possible combinations of 25 that involve Bob. Now I need to do the exact same thing with Susan, who has a score of 51. I need to generate all possible combinations of 25 people involving Susan. Then I need to do it for this person and this person and this person. I need to do it for every single person in there. Yeah, that's a lot of means. All right, so let's go back over here. I'm going to do it again. This time I did it and I got a mean of 44. Notice how far this 44 is away from the population mean of 50. This sample of 44 happens to be what we might call a bad sample, a non-representative sample. It's relatively far away from what the population mean is of 50. That means that the sample of 44 has a fairly large amount of sampling error, while a sample mean of, say, 51 has relatively less sampling error. So now what we're going to do is I'm going to speed things up a little bit. I'm going to draw a curve. If I were to go through and generate all possible sample means, and I'm filling in all of these sample means with dots now. These dots are like M's. It's just I can make dots faster than I can make M's. And all of this curve here is the distribution of sample means. Everything that's inside here, all of these, are all possible sample means. The mean of this distribution of sample means is 50. Notice that the mean of this distribution of sample means is equal to the mean of the population. That will always be the case. That's a good thing, because of all the possible sample means that I could get, the most common mean I could get is 50. It's the highest peak, right? There are more 50s than anything else that's possible. So that means I expect to get a sample mean. When I take a sample, I expect the sample mean to be the same as the population mean. That means I can, in a general sense, trust that sampling is going to give me a relatively accurate answer. Now notice I'm not 100% guaranteed that I'm going to get exactly 50. Scores around that are possible. But all of these have a relatively small amount of sampling error. They're pretty close. Now you can get some that are pretty far. Means out here in this area have a relatively large amount of sampling error. But those are relatively rare, whereas the means that have relatively small amounts of sampling error, the ones in the middle, are relatively common. They're more likely to happen. Okay. Another characteristic of this distribution of sample means is it's going to have a smaller deviation than the population. The population over here started with a deviation of 10, whereas the deviation over here has a standard deviation of 2. Now, this standard deviation over here has a special name. We don't usually represent it with that symbol. Instead, we represent it with SEM. We do that because it's the standard error of the mean. It's to remind us that the things inside this distribution are means, while the things inside this distribution over here are x's. Right? This is filled with individual scores, and this is filled with means. And as you learned from a previous video, means are less variable than individual scores. And that's why this distribution on the right is more compact. Its range is from 44 to 56, whereas the original population had a range of 20 to 80. So you can see that the distribution of sample means is more compact in terms of variability than is the original population. Now, the other characteristic I didn't talk about yet is the shape of this distribution of sample means. It's going to be normal. There are two ways that this distribution of sample means is going to approach a normal shape. First, as in the example I've just walked through, if the original population distribution, this one over here, has a normal shape, the distribution of sample means will always have a normal shape. So if this distribution is normal, this distribution will be normal, no matter what. The other situation in which the distribution of sample means will end up normal is if n, the sample size, is equal to 30 or more. If the size of the samples generating the distribution of sample means is equal to 30 or more, this distribution of sample means will have a normal shape, even if the original population is highly skewed like this. See, that's not a normal distribution. That's highly skewed. But if I'm sampling sizes, the sample size is 30 or more, each one of these means is based on 30 or more people, this distribution of sample means is going to have a normal shape. And I've already mentioned the center of the distribution of sample means we expect to be the population mean. It's the most common value anyway. And then finally, the spread of the distribution of sample means, I've said that it's going to be smaller, it's going to be less spread, but it actually follows a very specific formula. The distribution of sample means, the spread of that distribution of sample means, or you could say the standard deviation of the distribution of sample means, or we could say the SEM, is going to be equal to the standard deviation of the population divided by the square root of n. That is called the SEM, or the standard error of the mean. That is the typical distance that any given sample mean tends to be from the population mean. Does that sound familiar? It should. It's very similar to the definition we used for a standard deviation. A standard deviation is measuring the typical distance of scores, x's, from the mean. How far on average are all of these x's from the mean of the population? Well, the SEM is measuring how far on average each of these sample means are from the mean of this distribution, which also happens to be the population mean. So in a very real sense, this SEM is measuring sampling error. It's measuring typical or average sampling error. This SEM tells us, on average, how far all of these means vary from the population mean of 50. All right, now what I've drawn here is a distribution of sample means. It's really the same distribution of sample means that was on the previous screen. It has the same characteristics. It has a population mean of 50, population standard deviation of 10, and then I took sample sizes, a sample size of 25 to generate all these means. So this is the distribution of sample means that's based on a population with these characteristics and sample size of 25. So each of these means represents a mean of 25 people. And just like we've done with the population, we can take this raw score number line and convert it into a z-score number line. But we have to use this equation now. We have to use that equation because now we're dealing with sample means, not individual scores. And so what's different is this term down here on the bottom. That's the SEM, you may remember. We have to use that because, again, the things we're measuring are sample means, not individual scores. And they vary less, sample means vary less than individual scores, so we have to use a different formula. And that's what it is. So I'm going to do that for a score, a mean of 50. If I have a mean of 50, then I subtract that from the population mean of 50 and divide that by the SEM, I'm going to get a score of 0. Now I could do the same thing for 52. So it'd be 52 minus 50 divided by 2, and that's going to give me plus 1. 54 minus 50, it's going to give me 4 minus 2, that's going to give me plus 2. 56, so again 56 would go right there, minus 50, that's going to give me 6, divide by 2, that's going to give me plus 3, right? And then I can do it for the other numbers on the other side. Now I have a z-score number line, right? Now what's the advantage of having a z-score number line? Well, it allows us to answer this question. What's the probability of getting a sample mean of 52 or higher? What's the probability of getting a sample mean of 52 or something higher than 52? Well, in order to do that, we're going to do something very similar to what we did previously, except we're going to use this z-score formula rather than the one we've used before, because here we're asking about sample means, we're not asking about individual scores. So here's the equation. 52 minus 50 divided by the SEM gives me 2 over 2, which gives me a z-score of +1. And so what I'm interested in now is the probability of getting a score of a mean of 52 or more. So I want to know what's this area in here. How much of the curve is that area? Well, how do I do that? I use Appendix A. I look up a z-score of 1 in Appendix A. And do I want to look up in the tail or body column? Well, the shaded area is less than half, so that's going to be a tail. And then when I look that up, it comes out to be 0.1587, or slightly less than 16%. So slightly less than 16% of all possible sample means I could get with a sample size of 25 people will be equal to or greater than 52. That's giving me the probability that I'm going to have a sample mean that deviates this 52 or more from the population mean. All of this is telling me how many sample means are possible that have that much sampling error. So you can see we're estimating the probability of getting, quote, rare or bad samples. So now let's gonna ask you some summary questions that will see how well you followed the rather dense stuff we just went through. What is the standard error of the mean? If you need to, pause the video and see if you can generate an answer. You might want to go back and look at the previous screen again if you need to. What is the standard error of the mean? There are many ways to answer this question, but a good way is this definition. The standard error of the mean is the typical distance of all possible sample means from the population mean. And of course, the SEM, the standard error of the mean, is going to be impacted by sample size, n. As n increases, it's going to cause the SEM to decrease. That's simply saying that larger sample sizes have less sampling error, which makes sense. A larger sample size has more of the population in it, so it makes sense that it's going to represent that population better. The other part is it's the typical distance. In other words, you can think about it as it's what's expected. It's the amount of sampling error that you would anticipate on average occurring with a given sample size. Given the definition I've just described, what does the SEM actually measure that's really, really important? It's measuring the expected amount of sampling error for a given population and a given sample size. Again, the SEM is going to go down with a larger sample size, but it's really measuring sampling error, and that's why the SEM is such an important thing. Another conceptual question. How are the standard deviation and the standard error of the mean similar and different? Pause the video, see if you can generate an answer about how the standard deviation and the standard error of the mean are similar. Both the standard deviation and the standard error of the mean measure typical distance of something from a mean. That should give you a hint about how they're different. Pause, generate an answer. What are each of them measuring? The standard deviation is measuring the typical distance of what from the population mean? And the standard error of the mean is measuring the typical distance of something else. The standard deviation is measuring the typical distance of individual scores from the mean, whereas the SEM is measuring the typical distance of sample means from the population mean. So again, they're measuring similar concepts, it's just what they're actually measuring. They're both measuring variability, but one of them is measuring variability of scores, and the other is measuring variability of sample means. So the central limit theorem, that's where we started, and that's where we're going to end. The central limit theorem, it has three components, and it says that all distributions of sample means will have three characteristics. The first one deals with the shape. The distribution of sample means will approach a normal shape as n increases. When n equals 30, it's essentially normal. Do you remember the other situation when the distribution of sample means won't be normal? Even if the sample size is less than 30. It's when the original population has a normal shape. The second characteristic of all distributions of sample means is that the center of that distribution of sample means will always be the population mean. And again, that's important because it tells us that on average, we should expect our samples to give us the same answer as the population would. There'll be some sampling error, but because the shape is normal, we can use the z-score tables and formulas to estimate the probability of getting bad samples. And then finally, the spread of the distribution of sample means is going to be equal to the SEM, or the standard deviation, divided by the square root of n. And that is the standard error of the mean, which is a measure of typical or expected amount of sampling error. Now we've gone through a lot in this video, so it might be worth going back and reviewing some things or asking me some questions the next time you see me. But this is an important concept for the new and upcoming topic of hypothesis testing, which is a few lessons away.